Good morning, ladies and gentlemen. I'm Yijie. Today, I would like to present our paper entitled Towards Fully Automatic Scan-to-BIM, a prototype method integrating deep neural networks and architectonic grammar. The other two authors are Maosu and my supervisor, Dr. Frank Xue. And we are from Faculty of Architecture at the University of Hong Kong. So today I would like to introduce the automatic scan-to-BIM task and the international challenge we participated in the past 3 years. And then I will introduce our prototype method and the results, and with a brief discussion. So digitalization is nowadays a consensus to facilitate the whole life cycle of buildings, from design planning to construction to maintenance to demolition, etc. And building information modeling, the BIM model, is the container to hold many of these information stuff. So among the universal digitalization procedures, Scan-to-BIM is a rapidly evolving technology to enable large-scale and highly detailed building information modeling in terms of geometry, semantics, appearance information. Basically, with the LiDAR scanners or photogrammetry, we can capture 3D scans which are rich in details and appearance, which is also much faster than traditional survey. Oops. And a practitioner could convert these 3D scanners into parametrical building information models, which are commonly used in the AECO industry, which is highly parametric with semantics, and also is much more compact and informative than the 3D scans we originally scanned. But if we do this scan-to-BIM procedure manually, we actually need to create components and to register the template components to align the shapes captured by the 3D scans and handle a lot of topological issue. Actually, this procedure is very time-consuming. So we are thinking about the automation of scan-to-BIM procedure is really the key to populate this procedure and to add value this procedure in the field. So we participate the automatic scan-to-BIM challenging on the CVPR conference from 2021 to 2023. So CVPR is, the full name is Computer Vision and Pattern Recognition Conference, which is the top conference in the artificial intelligence and computer science, with a focus on the computer vision and 3D computer vision in terms of the point cloud processing and deep learning. So from 2021, there is a workshop named Computer Vision in the Built Environment. And this workshop is held for the researchers to share their experience about using the deep learning in many frontier automatic tasks from the of design and construction and maintenance, etc. And at the same time, this workshop also holds a scan-to-BIM challenge, where fully automation is required. So any manual editing or processing is not allowed in this challenge. That means our approach should handle all the steps from the input point clouds to the final reconstructed BIM model. So this challenging is based on a very large-scale data set. It contains about 91 floors of point clouds. That means each point cloud contains one individual floor of one building. And the number of points of each point cloud sample could be up to billion. And the things is mainly offices and car parks. So there are 2 tracks on this challenging. The first one is 2D track. That is to generate 2D floor plans. That means we need to predict the walls, doors, and staircases as lies in this floor plan. And the other track is a 3D track to generate 3D models containing the 3D instances of walls, doors, and columns. So here's our prototype method. Our prototype method named floor plan-based kernels and pillars of points. In short, is FLKPP, named after some important components in our method. So our method is try to integrating the deep neural networks, DNN, and the architectonic grammar. So basically, we want to do the semantic parsing, extract a lot of semantics from the point clouds by using the DNN, which is very powerful at this stuff. And we also use some architectonic grammar. There's some regularities in the architecture to implement the pre-processing and post-processing to initiate the learning and refine the prediction of learning. So if we look at this overview chart with a given input point cloud, we then do the pre-processing to cluster rooms and then remove the clutter in the rooms. And then we feed this clean data into the learning procedure in separate two track for the 2D and the 3D. And then after that, we do some post-processing to fix the topological issue and do the parametric reconstruction from the raw semantic segmentation result. So let's see in more details. And for the first step is the pre-processing. This step we try to do the room cluster and also remove the noise. So we basically visualize the whole space, and then we label the voxels. They are close to the edges or horizontal planes. Actually, they are ceilings or floors. And then we use the region growing to cluster these voxels into rooms, and then remove the clutter inside the rooms. And then after that, we can gain a relative clean point clouds. With that point cloud, we feed this data into two individual branch for the 2D track and the 3D track. And for the 2D track, this is the upper figure. We project the point clouds onto a horizontal 2D grid, and then we generate some images, for example, with RGB channels. And each channel is actually represents the point distribution of different heights, such as 1 meter layer above the head level or 1 meter layer below the head level. And then after that, we have some images, and then we feed these images into a network named LCNN, proposed in 2019, and then to predict the corners and edges, and then generate a coarse floor plan like this one. And then for the 3D track, we use KP-Conf proposed in 2091, and this is a S.A.R DNN for 3D semantic segmentation. And then we segment the point cloud into 4 types, including the walls, doors, columns, and clutter. So after that, actually, the 2D prediction of lies contains there are some missing parts in the results, and some walls didn't connect to each other. So we then extend the lies based on the line map predicted by the LCNN or the roadmap cluster in our pre-processing. And for the 3D track, we further segmented the instance from the classified points and then estimate the bounding box of each instances to create the parametric primitives for each instance. And this is our result in the 2022 challenge. We ranked second in the 3D track and third in the 2D track. So for the 2D reconstruction task, the matrix is measuring the endpoint matching of the lines of the floor plans. So there are some precision and recall metrics here. And the matrix also measure the intersection over union. So it shows IOU of the rooms predicted and the ground truth rooms. And the warping error and the Betty error is also measuring the topological errors. So we are ranked the third one, and we could see actually the points matching, endpoint matching is very challenging, so all the entries just gain very low precision here. And for the 3D reconstruction, the matrix is the 3D intersection over union of the 3D instances. So our IOU here is on average about more than 20%. So we also noticed that actually the IOU of the raw 3D semantic segmentation could achieve like higher than 80%. But when we calculate this in object level, there could be a large gap. So we think this is very challenging because there are some occlusion, missing part, and noises in the point cloud and the 3D semantic segmentation. So here's some visual results of 2022. This is the 2D results. And we could find most of the walls here, but there are still many topological issues or some missing parts here. And then this is a case of car park. Actually, the point cloud could contain a large portion of the noise, so this should be removed in the pre-processing. And this is the 3D results of 2022. Okay. And after introducing our method and results in 2022, we also participating this year, so we just want to brief some updating of our prototype method. So we update our pre-processing in 2022 by applying some simple machine learning methods to try to make the room segmentation more precisely. And then we also use simple machine learning method to classify to identify the real rooms and remove the rooms that actually contain some outdoor noise. And the updates in the 3D learning in 2023, we test more 3D SOTA DNNs for semantic segmentation, like we add the point contrast and the point nets proposed in 2020 and 2022. And we found there are no perfect DNN right now that could do very well in in all categories and with different settings. So we try to integrate different DNN methods results based on their confidence and to have a higher quality 3D semantic segmentation results. And for the post-processing, for the 2D track, we do some orthogonal connecting and merging lines to reduce the line numbers and then do the semantic breaking based on the results of semantic segmentation. And then we also try to adapt the wall and door column, their 3D boundaries to make the reconstruction more accurate. And this post-processing is mainly based on some regularity, some rule-based, but they are very useful and direct to improve our metrics by a large margin. So here's this year's result. We finally ranked first in the 3D track and the second in the 2D track. So you could find that actually most of the metrics is significantly improved in this year. And then this is some visual results. 2D results, there is high IOU. And there are also some cases that we cannot handle very well, such as building with shapes, such circular shapes, so it's very rarely in the training data. So both the learning and the post-processing or pre-processing cannot handle this case very well. And this is the 3D results. The left part is the case of office, and the right part is for the non-office. So based on our experience on participating in this challenging and the method development, we have some findings, but due to the time limit, I can just share one point. Actually, nowadays the DNN is evolving very quickly to and show very strong power to do the semantic segmentation and even 3D reconstruction. So we really want to integrate this powerful DNN in the automatic scan-to-BIM procedure. But there are some data issues here if we want to really transfer DNN from computer vision field to the AECO industry. For example, in the computer vision field, they mainly use some much cleaner point cloud to do the 3D segmentation training. So if we want to guarantee the results of 3D semantic segmentation by the SOTA DNN, we need to firstly segment the whole floor of point clouds into different rooms and try to clean some of cluster inside the rooms to make the learning easier. And then another issue is in the 2D track, the organizers, they use the as designed floor plans as the ground truth and label the 3D point clouds. We know that actually there are a lot of inconsistencies between the floor plans and the 3D point clouds. So this inconsistency also brings some instability in the 2D training. So, but we may also some other thinking that actually we can do the whole automatic scan-to-BIM in an end-to-end way. So we may not need to design very specific steps. We may also fit all the data into the net and then come up with some satisfying BIM model. This could also be possible, but maybe specific design is needed. So for the limitations and future work, we would like to improve the closeness and figure out the topological issue in our current results and maybe have a better clutter removal algorithm and also improve the endpoint matching of floor plans. And also we also want to try to automatically complete the missing part of point clouds and the reconstruction. Thank you, that's all.